tutorial. This tutorial will be part of a series, and in the series we discuss the way that Rat calculates the magnetic field and how the element size and calculation settings affect the accuracy of the results, and so what's important when you are setting up calculations in Rat. The first video in the series is about Rat and the multi-level fast multiple method. I will start with a short presentation on the multi-level fast multiple method, and then I will show you how the settings in the Rat GUI can be used to control the accuracy of your calculation. So first, what does it do, the multi-level fast multiple method? So it's an algorithm that basically was intended to highly efficiently calculate long-range interactions in large systems. And basically that means that, for instance, it can be applied to electrostatics at long range, where you have this 1/r dependency of the electrostatics field potential here, but also gravitational potential, which is given here. You have this same 1/r Green's function, so which is what they are called, that it can be applied to the multiple method. And in magnetostatics, there's a trick, because if you use the vector potential sort of variant of the Biot-Savart law, which is written here below, this has the same 1/r Green's function form, and that you can use for the fast level multiple method. So how does that work? When you take the vector potential A, it's governed by the nabla of A equals μ0 times the current density vector. Now, this is a Poisson equation. However, outside the current carrying region, so outside of your coil, there's no current density, and this simplifies to the gradient of A equals 0. That means that each component, AX, AY, and AZ, individually satisfy the Laplace equation. And therefore, this Laplace kernel, 1/r, can be expanded to spherical harmonics. And that's an important point, because inside the current region, this equation is not valid. You cannot use the solution of the Laplace equation for when this is not 0 is not spherical harmonics, and that's a very important point. So that's why it's valid. And so these spherical harmonics, they can actually be used to represent the field as complex as is needed, because basically there's a literal translation from spherical harmonics to field, because a dipole is like the second order spherical harmonic, and then you get the sextupole and the quadrupole and so on and so on. They are all higher order spherical harmonics, and so if you add them together with different coefficients, you can basically represent any field that you're calculating. But again, it's important to say that this J0 criterion means only because your J is 0 is when you can actually do the spherical harmonics expansion, and this Laplace equation is satisfied. So that's important. Now, that also means that you still need Biot-Savart for nearby sources. So MLFMM is only accurate for well-separated source-target pairs where the field is smooth and the multiple expansion converges rapidly. So when a target is close to a source, the field varies rapidly because the target and the source are close by, and therefore the expansion initially becomes inaccurate, and when it's too close to the current, it's even invalid. So for far field interactions, you approximate your system with multipoles and local poles. And for near field interactions, you still do a full Biot-Savart computation between the source and the target. And this hybrid approach means that you gain a lot of speed during your calculations, and that's what's being used in Rat. So how does that work? There's multiples and local poles in the multiple method, and these are used to represent the field of the sources. So a multipole represents the field of a source inside a sphere, here on the right, that is at any point, so the sources are inside the sphere, at any target point outside the sphere. So the field of this one on this target. And so it compresses the field into a few components of the Legendre polynomials. The local pole, here below, is basically the field of a source outside a sphere. So this is the source outside a sphere at any target point inside a sphere. So this is a local pole. And therefore, multipoles and local poles are essentially opposites from each other. So you have here the multipole where the sources are inside the sphere, pointing to a target outside, while a local pole is a source outside the field, a sphere pointing to the targets inside one. So how does this reduce the complexity of your calculation? Well, basically, if you consider a system with n sources and m targets, if you do the direct Beer-Savart method, you will have to calculate the field from each source on each target. And so you need to do n times m calculations. And that's represented in this illustration. Direct Beer-Savart, therefore, has n times n complexity. If you go to the multipole method, on the other hand, since the multipoles are a collection of sources and the local poles are a collection of targets, you in fact reduce the complexity to a linear system, n plus m, not n times n. And that's how you gain a lot of speed, because you don't need to do as many calculations. Now, these multiples, you can do some operations on them. So you can make them rather large, at larger distance between multipoles and local poles. You can include more and more sources in your multipole. And the more sources are in there, the less calculations you need to do. It's important to note that these spheres, they're not allowed to intersect. And the reason for that is that the multipole method is not valid at the place, at the region where there's current, is what we said before. So if your source is intersecting with your target, that means you're in the current area and the multipole method can no longer be applied. So at the same time, you can also combine different multiples, like is illustrated here, into a larger multiple group. And you can do that as long as this large sphere does not intersect with a local pole. And so you can do all kinds of combinatory steps to further and further reduce the number of calculations that you actually need to do. Then how do you apply this to your coils? Basically, you take your model and you start subdividing the sources and targets into these multipoles and local poles. And you do that by placing them in an octree. That's the technical name for this. It's shown here below. So you take all your sources and targets. So the collection of sources would be your coil, and the collection of targets would be the location where you want to calculate the field, which could either be the mesh of your coil or a plane or so and so on and so on. And you start at level 0, where you place a massive box around all. This is a 3D box, by the way. You place a massive 3D box around all sources and targets. And then you start to divide them in smaller boxes. Every time you divide them in 4 smaller pieces. This subdivision doesn't continue forever. There are a few stop criteria, but one of the stopping criteria is you basically set a number of sources or targets inside the box that can be inside, and then you stop. In red, you can also do the average number of sources inside the boxes where the refinement is stopped. So that's a setting that we will see later. And each box stores at least either one multipole or one local pole per dimension. And here I mean AX, AY, AZ. So that means that in each box there is at least 3 multipoles. There can be boxes, for instance, if you continue dividing here, if you would divide this box, this one in the corner, that would be an empty box. This is not stored in the octree because it's empty, and that reduces basically the calculation speed and also the memory that you need to have to store all these boxes in. So if they're empty, they're not stored in the octree. Then the core of the multiple method. You will go and walk through the tree and do your calculations. And it's in this order as on the slide. So first you go from source to multiple. So at the leaf level, you convert the sources inside the box into a multiple expansion. So that's step 1. That's shown illustrated over here. Then you go to step 2, where you go from multiple to multiple. That means you move up the tree, you shift and combine multiple expansions from child boxes, so here these are the child boxes, into one multiple of the parent. Then the most heavy computation heavy step is number 3, where you go from multiple to locable, because that is where for each box, as is shown over here, you convert your multiple expenses from well-separated boxes into local expansions. So that's why you do your calculation. This is the core of the fast multipole method, and it's compressing basically all these long-range interactions. The next step, and it's a symmetric process more or less, so this one is more or less symmetric with step 2 and the last step with step 1, is you move back down in the tree and you go from your locable expansions from the parents to the children to increase spatial resolution. So here you were in a parent box and now you go back to the children. And then finally you go back from locable to target, where at the leaf level you evaluate the local expansion at each target point to compute the field. And so that's basically full circle how the multiple method works. Now, there's one last step, because here we said, you need to do your multiples. Multiples work outside the current region, but boxes that are direct neighbors of each other and also places where there's current, you need to do direct BSFR. The exact BSFR is used basically, which is illustrated here. So if this is your target box, for these in 2D 9 boxes surrounding it, you need to do direct BSFR, because the short range interactions means you need to do BSFR. And for the other ones, so for the higher levels, you can use the multiples. And that's illustrated here. So the circles, these are multiples. And these local poles are the targets, the stars that are indicated. And so the combination of doing direct BSFR nearby and multiple expansion at the far end, where you have all these harmonics describing your field, is basically what makes your multi-level fast multipole method so fast in comparison to direct BSFR. One important note on the refinement of the grid is the more you refine the grid, usually, the better the multi-level multipole method works. So during the refinement phase, where the source targets are divided in boxes, the division stops if the largest element can no longer fit into a small box. So here you have an element basically that would no longer fit into just a single box, and then the algorithm says it stops. But if you notice here, it's only long in 2 dimensions, so it's a very thin box. And so if you make this your elements actually more cubic and not so long or pencil-like, the multipole method can do a better refinement, and a better refinement usually means a faster calculation. And therefore, a finer grid might actually make your calculation faster, even though this is slightly unexpected, because usually when people are used to doing finite elements methods, people expect that the more elements you have, the slower your calculation, and therefore usually people try to make use of symmetry, like making pencil-like, so very long elements, and that's not very suitable to the multipole method. So for the multipole method, you should try and keep your elements more cubic-like or round-like in all 3 dimensions, and bigger elements don't necessarily make it into a more accurate, or actually it makes it into a slower calculation. The logger is actually showing the refinement. So if you see that it stops refining at level 3 or 4, you might want to do something about your element size. And then you can try and aim for a refinement up to level 5, well, up to level 8, but somewhere between 5 and 8. It's important to say that the more detail you have in your model, so if you have very fine bends in your wires, for instance, you would like to aim for a higher refinement level. All right, so now how does that work in practice? Let's look at this coil, for instance. This is just a simple racetrack coil, and we're gonna add a plane calculation here. And let's do it in Y. Well, it doesn't actually matter. Anyway, the multi-level fast multiple settings are under the calculation settings. So for each calculation, there are these multiple settings. And if you want to do a very accurate calculation, you click on Direct Beersavar. Then all the other ones, all the other settings are not taken into account anymore because it's not a multiple method anymore. So let's say, well, this is very accurate, but also very slow because you go from this n plus m complexity to n times n. So let's assume we want to do the multiple method. So we have a faster calculation. If you want a more accurate calculation, you should make sure that you have an extended interaction list. This is what is meant here, is that the nearest neighbors here, so it does not only do the nearest neighbors, the Beersavar there, but it takes a few more nearest neighbors. So in 3D, actually, if we go to this paper from Mr. Korzak and Petit, paper is called Fast Multiple Methods for Particle Dynamics. They show a picture, actually. They have a picture. So in 3D, the nearest neighbors would look like this. So this would be the extended interaction list. And so all these elements surrounding this this block in the middle, which is your where you are situated at the moment, so where you're calculating from there to there, this is the extended interaction list. And so you take more elements surrounding it to do direct Beersavars, and that makes it more accurate. And this is the number of expansions. That's basically means how you approximate your field of your multiple. So if you can do like 10 expansions, of course, your polynomial will be more accurate than if you do only 2 expansions. And so basically, to demonstrate this, I want to actually mess up the calculation. So in fact, I'm going to not use the extended interaction list and only do 2 expansions. And then I make a rather large box. So for the plane calculation, I do a 10-meter plane calculation with 1,000 times 1,000 elements. So target points, basically, because this is the discretization of your plane. So this plane will be divided into 1 million little boxes, 1,000 in this direction, 1,000 in that direction. And so the result is as follows. Let's zoom in a bit. So I look here at the heat map, but when you go and look at the tiny values, I'm going to even make it tinier. Yes. So when we only consider like very low field ranges, so I zoom the color box in the color map, I zoom it in such a way that we only look at where the field is like extremely tiny. You see here that there is a very inaccurate calculation because this is not what the field should look like. It shouldn't have this sort of strange round gradient in one square here. In fact, it shouldn't have these squares at all. And so what you see here is, in fact, in each square, you see the gradient, and this gradient is your harmonics, basically. So this is the Legendre polynomial in this area for the settings that we have. And so these squares, they should disappear if we in fact go and use the extended interaction and go back to 5 expansions. So if we now do the same thing, so I change the color bar in such a way that we only look at the very low field. See, now these squares are gone, because now we were able, first we have the extended interaction list. So if you're close to where you're calculating, you actually take a larger range for when you do direct Biot-Savart. And in addition, not only do we do that, but we also have larger expansion of your polynomials so that your field description is even more accurate. So that's those 2 settings. Now, the octree refinement is basically the other part of the multipole method that's exposed to the users in red. And basically it stops refining here. So it stops making the boxes smaller and smaller if there's geometrically averaging about 128 sources and or targets in these boxes. So it takes the average, the geometric average. You can do others. So you can say either stop refining when there's both 128 sources and 128 targets in the box. Either is also a stop theorem that you can play with. You can take the average, you can take the squared number of sources plus squared number of targets, and you then do the square root of that as the average 2. You can do the times, but from trial and error and from experience, basically, it was found that the geometric mean, which is the default, and then 128, although this you can play with, in fact, if you want more refinement, is what I said, then this is a setting you can also play with. Because if we go and look at the logger, you might actually understand the logger a bit better now after this tutorial. You see that here is the refining of the grid. So in fact, in this case, we have refined until level 7, which is good because I said like you want to aim for somewhere between 5 and 8. So this is a good refinement. If it doesn't reach that, we can say, oh, let's do 50. And now here, it's already done. So at least it didn't really mess up. Yeah, here now we went to refinement level 8. So we went much further. So that's what we did by changing this. I think in general, these settings have been chosen so that in general, you should be fine. Also, we talked about the actual multipole method, how it goes from source to target, source to multipole, multipole to local pole, multipole to multipole, and so on. And so it does that for like all the levels and then back. So this is how it basically moves up and down the tree for these different multiple steps. And that is this logger explained. So important settings, basically extended interaction list and number of expansions. Now, for different types of calculations, because for instance for cylindrical harmonics, you see that in the plane calculation, the default was 5 and extended interaction list was set. Here, the default of expansions is actually set to 7. So for very high accuracy demands, Rat already has some different settings here. If we go to the mesh calculation, actually the extended interaction list is not even turned on. It's just 5 expansions, and that's already accurate enough. So that's already taken into account in the default settings, basically in Rat, that for some calculations like the harmonics you need very good accuracy, and therefore you want higher number of expansions, while in the plane calculation and other calculations 5 is fine. You still want to have an extended interaction list, but for the mesh calculation it's less necessary. All right, this is what I wanted to show you today. for how the multipole method works. In the next video, I'm going to explain the source type. So you can set in the coil, you can change the source type and the target type. And this also can affect the accuracy of your calculations, but that will be the subject of the next video. Thank you for watching.